All right, just a refresher. The ozone layer, when you reference the ozone layer, you're referencing a layer where? Where?
Right there.
In the stratosphere. Thank you. Now, can ozone be found anywhere else besides the stratosphere?
A little bit.
A little bit. In the troposphere, we learned this in the beginning of this unit. When ozone is in the troposphere, it's bad, it's like toxic. When it's in the stratosphere, it's good. It's a shield that protects you against UV rays. So without the ozone, UV rays, which are ultraviolet light rays, will come straight down to Earth. Instead of, let's say, if I'm going to draw, let's pretend this is ozone right here. So UV rays that are coming down from the sun are going to come straight down if there's not an ozone molecule. Versus if it goes through ozone, it's kind of torn apart and they're weakened, okay? So ozone is like the sunblock that's naturally occurring on Earth, and because of our activities on Earth, we've made a hole in it and we're causing UV rays to come straight down. And there's more damage to plants and single-celled organisms than there is to humans, but there is direct effects to humans, such as cataracts and skin cancers. Our skin is our first layer of protection, and without that, we're going to see more problems. All right, so what caused this problem? The main thing is CFCs. I'll make that bigger for you to see. CFCs, actually it's right here, which are called chlorofluorocarbons. Other possible contributors are halons, and that's all I want you to know for this test, okay? And we're going to focus on this. This was so severe that if you look at this graph right here, when they first discovered the hole in 89, for now, it only took 89 to 96 to ban this chemical worldwide. I mean, in the United States, not worldwide. That would have made a big impact. So the United States banned the use of CFCs. In 89, they were literally going to stop producing aerosol cans. Stop, because they didn't know how they could make an aerosol can without CFCs in it. Then they figured it out, so aerosol cans still exist. But you'll look at them, and they have a little triangle, and it says ozone friendly. So besides aerosol cans, what else produces CFCs in the atmosphere?
Chlorine.
Well, that's part of CFC. Chlorofluorocarbon. You get it? What puts that compound in the atmosphere? Refrigeration. All coolants. Also foams. And so your packaging material in the past used to be full of CFCs. And solvents have CFCs. So our biggest problem with CFCs today is still in the cooling systems, okay? But completely banned from aerosol cans. No aerosol can produced contains CFCs. You'll see two things, a triangle that says CFC friendly or ozone friendly. So we banned CFCs, good thing, right? Obviously somebody said this is a serious problem, we better get on top of it. The problem is, this compound, chlorofluorocarbons, does not break apart. Nothing reacts with it. So it lingers there, and it could stay there for a long period of time. So it's a big deal. We can't pour things out into the atmosphere so CFCs will react with it and break apart. They're just there waiting to deplete ozone. So how does this happen? Is the next slide. I'm going to teach it to you as a 3-step reaction. Now, chemistry is a prerequisite for environmental, and I've watered it down the whole way. This reaction you have to know, okay? You're not going to know it as a balanced reaction, but you're going to know initial compounds and destroying contributors. So, what starts ozone depletion? Everybody should be able to answer this. What starts it? CFCs. Come on, guys. Stay with me. Here's my CFC. CFC stands for chlorofluorocarbon. The only thing that breaks apart a CFC, ironically, the thing we're trying to protect it from is UV. So ultraviolet light hits CFCs, and what gets broken off?
The chlorine.
Chlorine. We're gonna stop right. What's gonna be the start of step 2? So who's staying with me? Chlorine. What was left over in step 1? Chlorine is gonna react with, what's that purple thing there?
The
Oxygen.
No.
The O3.
What's O3?
Ozone.
Ozone. Chlorine reacts or bumps into or combines with, whatever words you wanna call it, with ozone. And what happens? Look at the picture.
It takes off the oxygen molecule.
So no more what? Ozone. There goes your ozone. I will. So it steals an oxygen, forming chlorine monoxide, and you're left with oxygen gas. So I'll pause and go. Repeating step 2. Chlorine reacts with ozone right here. It takes away an oxygen, forming chlorine monoxide, and oxygen gas is left over, so no more ozone. At this point is where the ozone depletes. So what do we have now?
When a free atom of
You have 2 oxygens.
We have oxygen gas, which we know we breathe in, so there goes that. And what else?
And oxygen and chlorine.
Chlorine what?
Oxygen.
Chlorine
Oxide.
monoxide. So my start is right here, chlorine monoxide. Actually finds an oxygen that's just floating around. Chlorine monoxide collides with oxygen, whoops, and forms what? Look at the picture.
And forms 2 oxygen.
An oxygen gas and what else? Look at the picture. Look at your picture. Don't even look up there. What is this? Right here.
What? The 2 oxygens.
This, what I just pointed to.
Chlorine.
Chlorine. Now, I just pointed to chlorine. Who could tell me what do you think can happen next?
After this,
It's gonna collide with the 2.
I'm gonna pause. So what happens with this leftover chlorine, it's gonna go back and start this depletion process again. It looks for more ozone, and believe it or not, one single chlorine can destroy 100,000 ozone molecules.
It says the 2 oxygen